In this lecture, we're going to discuss a systematic way of determining when your set of functions is linearly independent. And to get there, we need to review a little bit of information about matrices and determinants. So, matrices and determinants. So first of all, a table or an n by m table of numbers is an n by m matrix. So for example, if I have A equal to 1, 2, 3, 4, this table has 2 rows, 2 columns, so that is a 2 by 2 matrix. If I have B equal to 1, 2, 3, minus 2, 1, 6, then that is 2 rows, 3 columns, 2 by 3 matrix. And if I have, I don't know, D equal to minus 1, 1, 6, 0, 1, minus 1, 2, 3, 5, that is a 3 by 3 matrix. And so on. I can write 10,000 by 50 matrix, whatever. If n is equal to m, then we have a square matrix. So then A and D on the previous page are square matrices. While B is not a square matrix. Okay, number 2, given a square matrix, we can define its determinant. And we're only going to talk about 2 by 2 and 3 by 3 matrices, but whatever I'm doing here can be extended to n by n matrices. So if A is a 2 by 2 matrix, A is equal to A11, A12, A21, A22, then the determinant of A is going to be equal to the product of elements on the main diagonal minus the product of elements on the secondary diagonal. So it's going to be A11, A22, minus A12, A21. So for example, if I want to find the determinant of 2 minus 1, 1, 3, then that is going to be 2 times 3 minus 1 times 1. So determinant is 7. Another way to write determinant is to use, instead of parentheses, large parentheses, just vertical lines with the matrix. So 1, 2, minus 1, 6. This determinant is 6 times 1 minus 1 times 2, and that is 8. Nope, not 0, 8. All right, so A, B, C, find the determinant of the matrix A equal to 5, 0, 1, 6. I can write the answer in two ways. Determinant of A, right? That's one type of notation. This is 5 times 6 minus 1 times 0. This is equal to 30. Or I can label it as the same table but with vertical lines. This will also stand for the determinant 5, 0, 1, 6. Still 5 times 6 minus 1 times 0. And that is still 30. Okay, so that is a 2 by 2 determinant. So then the second part, all right, let's make this 1, that's 2 by 2. And now 2, if A is a 3 by 3 matrix, then we're going to use the following procedure. So let's say I want to compute the determinant of A11, A12, A13, A21, A22, A23, A31, A32, A33. So that's a 3 by 3 matrix, and notice that the notation that I'm using, the first index always represents a row, and the second index represents a column, right? All second indices are 1, all second indices are 2, all first indices are 1, all first indices are 3, and so on. So the way we're going to do this is going to be as follows. So what we will do is we will take the first element in the first row, A11. We take that, then we cross out the first column that contains element 1, 1. We cross out the first row, which also contains element 1, 1. And if I do this, then what is left is, so the elements circled are gone, and what is left is just a 2 by 2 matrix. And I'm going to take a determinant of this the determinant of this 2 by 2 matrix, so it's A22, A23, A32, A33. Then you repeat the same thing for the second element in the first row. You remove the first row, which contains that element, and you remove the second column that contains that element. So everything circled is gone, and what is left is a matrix, 2 by 2 matrix A21, A23, A31, A33. And so we're going to take A12 and multiply it by that determinant, A21, A23, A31, A33. And in this case, we're going to put a minus sign in here. In the future, what tells you where you put minus sign, where you put plus sign in this procedure, you look at the indices. If the sum of indices is even, you put a plus sign. If the sum of indices is odd, like in this case, 1 plus 2 is equal to 3, you put minus sign. And so then only one element remains in the first row, and that is A13. So we do the same thing. We remove the first row and now the last column that contains element 1, 3. A13 has indices 1 and 3. 1 plus 3 is even. So we're going to put a plus sign and then multiply it by the determinant of the matrix that remains when you remove the first row and the last column. So plus A13 times the determinant A21, A22, A31, A32. And that's it. So when you compute this, you get a number, and that number is a determinant. There are many ways in which you can compute this 3 by 3 determinant, but I'm just going to list one because we don't need to know much about determinants in this course. So let's do an example. Example, let's say A. I want to find the determinant. Find determinant of A if A is a matrix like this. A is 1, 0, 2, 1, minus 1, 1, 2, 3, 1. Okay, so what is the determinant of this? So either again, the same notation, either I write determinant of A, or I put exactly the same table into, I bound this table by vertical lines, and then that means that I'm talking about the determinant. So what's the determinant of A? You take the first element, 1, and you multiply 1 by the determinant that remains once you remove the first, by the determinant that remains once you remove the first column and the first row. And so that is going to be minus 1, 1, 3, 1. Then you have 0 times the remaining determinant, but because it's 0, I don't care what the determinant is because I'll be multiplying it by 0. And then I have 2, and 2 needs to be multiplied by the determinant that remains once you cross out the first row and the last column. So plus 2, right? What are the indices of 2? It's in the first row in the last column. First row index 1, last column is index is 3. 1 plus 3 is 4, so then we use a plus sign. So 1, minus 1, 2, 3. And so this determinant then is going to be 1 times minus 1 times 1 minus 1 times 3, right? That's a 2 by 2 determinant here, plus 2 times 1 times 3, second determinant, minus 1 times 2. And so this should be 1 times minus 1 minus 3 minus 4, plus 2 times 3 plus 2. So 2 times 5 is 10 minus 4, 6. So this determinant is going to be 6. And let's do one more example, B. I want to find the determinant of the matrix 5, 1, 2, 1, 0, 0, 3, 4, minus 5. Follow the same strategy. Take element 5, which sits at the 1, 1 position, and multiply that element by the matrix that you'll get by deleting first row in the first column. So that would be 0, 0, 4, minus 5, minus 1, the second element in the first row. Now remove the first column in the first row in the second column, and the remaining matrix is 1, 0, 3, minus 5. And then lastly, you have 2, and a 2 by 2 matrix that you get by removing the first row in the last column is going to be 1, 0, 3, 4. And so now calculating all of these 2 by 2 determinants, we have 5 times, well, that first determinant is 0 times minus 5 minus 0 times 4, 0, so it's 5 times 0, minus 1 times minus 5 minus 0 times 3, plus 2, 1 times 4 minus 3 times 0. So nothing here. This parenthesis is minus 5 times minus 1 plus 5. And in here, 3 times 0 is 0, so 4 times 2 is 8. 8 plus 5 is a lucky 13. Okay, so we can compute 2 by 2 determinants by now and 3 by 3 determinants. And so now let's go back to ODEs. And here is the result that we're going to use both now and later on in the future. And the result is this. So let's suppose that I'm going to write this down by using the example of a third order equation, but the same thing is going to work for any order. So suppose that y1, y2, y3 are solutions of a3 of x, y triple prime plus a2 of x, y double prime plus a1 of x, y prime plus a0 of x, y equal to 0. So there are solutions, 3 different solutions of a third order homogeneous equation. Then the set of solutions y1, y2, y3 is linearly independent if the following determinant y1, y2, y3, y1 prime, y2 prime, y3 prime, y1 double prime, y2 double prime, y3 double prime, so that is a 3 by 3 determinant, that this guy is not equal to 0 for all values of x. Now, this determinant is going to have a special name. We're going to call it the Wronskian of y1, y2, y3. So, whenever you found the solutions of your homogeneous ODE, how can you determine if they're linearly independent? Simply by computing the Wronskian. So if the Wronskian is never zero, then that means that your solutions are linearly independent, and then you can form a general solution out of it. So then y equal to c1 y1 plus c2 y2 plus c3 y3 is a general solution of the ODE. Okay. So let's now do a couple of examples of this. Let's suppose I have an equation. So again, let me emphasize it that if I have a second order equation, so for the third order equation, we're getting 3 by 3 matrix. For the second order equation, I should get a 2 by 2 matrix because there I only need two solutions. And then what would be left is just this 2 by 2 determinant. If I have a fourth order equation, then I'll have to evaluate fourth order determinant, fifth order equation, fifth order determinant. But we're not going to deal with anything which has size more than 3. So let's look at the example of 2 by 2 determinant or a second order equation. So let's suppose that y double prime plus y equal to 0. And I want to show that y1 equal to sine x, y2 equal to cosine x are linearly independent solutions of the ODE. Okay, so two things that I need to do. First of all, I need to show that there are actually solutions. And second thing that I need to do is to demonstrate that those solutions are linearly independent. So part A, to show that there are solutions, y1 prime is cosine x, y1 double prime is minus sine x, y2 prime is minus sine x, y2 double prime is minus cosine x. So therefore, if I take y1 double prime and I add y1 to it, y1 double prime is minus sine x, y1 itself is sine x, this is equal to 0. Y2 double prime is minus cosine of x, y2 is cosine of x, so once again, if I add those together, I'm going to get zeros. So the conclusion from this computation, y1 and y2 solve my ODE. So next I need to demonstrate that they're linearly independent. So W of y1, y2 is going to be what? It's y1, y2, y1 prime, y2 prime. In this case, y1 is sine x, y2 is cosine x. Then y1 prime is cosine x, and y2 prime, the derivative of cosine, is minus sine x. We have to evaluate the 2y2 determinant. So sine x times minus sine x, product of elements on the main diagonal minus the product of elements on the secondary diagonal. So cosine x times cosine x. So what is that? That's minus sine square of x plus cosine square of x, which is 1. So minus 1, never equal to 0. And so that means that y1 and y2 are linearly independent. And if they're linearly independent, then that means that I can form a general solution out of them. Y of x equal to c1 sine x plus c2 cosine x. This guy is a general solution of OD. Now, more generally, any n linearly independent solutions of the nth order linear homogeneous OD. These n solutions, we're going to say that they form a fundamental set of solutions. Now, what is exactly fundamental about them? Just this fact that we have already been using, that out of these n linearly independent solutions, I should always be able to construct a general solution by taking a linear combination. So therefore, for example, here, sine x and cosine x, they form a fundamental solution, set of solutions of ROD. Okay, then in the next lecture, I'm going to give you more examples of this, and then we'll talk a little bit about what do you do when you consider non-homogeneous ODEs.